Okay, guys, so notice that this error is much smaller than the one before, right? And this is what we said last time. This error is much smaller. So we see that our absolute error is going to be the third derivative of f evaluated as z divided by 3 factorial times h squared, right? And if h is a small value, then it's going to be, this absolute error is going to be much smaller than the one for the forward difference or the backwards difference, right? Because suppose if h was 1/10, right, then this will be 1 over 100, right, which would be much smaller than 1/10, right? So this is where, and here where z maximizes the absolute value of the third derivative on the interval from x minus h to x plus h, because essentially we're using those as my endpoints, right, to approximate my derivative here. Okay, so let's look at an example real quick. This will be the last thing we talk about today. Okay, here it is. Approximate f prime of x for f of x equal to e to x at x equal to 0 with h equal to 0.1. Now there's our 1/10 right there. Using, in this case, we're going to use the forward difference, which is f prime of x approximately equal to f of x plus h minus f of x over h. Let's use that other difference, and then we're going to use the forward difference again, where we have 2h instead. And then we're going to use the midpoint difference. We use f of x plus h minus f of x minus h over 2h. So we're going to use all three of these guys. Okay. Now let's do this. Now what is the actual value of the derivative at x equals to 0? What's the derivative of e to the x? That's a good question to ask ourselves. The derivative of e to the x is e to the x, right? If I plug in 0, that equals 1. Okay. Now let's see how well all these functions have done, right? So let's plug in. We're just going to go to the side here. Okay. Here I want to do f of x plus h. My x is 0, so I have e to the x, which is 0, plus h, which is 0.1, right? Minus e to the x, which is e to the 0. All that divided by 0.1. Now, if you work that out, you get about 1.05171. Not an approximation, not a bad approximation from of our derivative, which is 1, right? If we try the next one, f of x plus 2h, right? This is going to be e to the x, which is 0, plus 2h. 2 times 0.1 is 0.2 minus e to the 0 divided by, in this case, instead of h, we use 2h, which is going to be 0.2. Now, if you work this one out, you get 1.10701. Well, that's worse, right? That's a worse approximation to my derivative at 0, right? That's no good. What about the last one here? My midpoint difference formula, right? F of x plus h, so let's do that. It's going to be e to the 0 plus 0.1 minus f of x minus h, that'll be e to the 0 minus 0.1, all that divided by 0.2, right? And if you work this one out, you get approximately is equal to 1.00167. And this, of course, is our best approximation. Best approximation. Not too bad, not too shabby, right? So this is what we're looking at here, right? And what we want to do next time we meet, right? Next time we meet is we want to talk about error analysis, look at the second derivative and things like that. But for right now, I think this is a good place to stop, and I'll try to work out any more of these bugs that I have with working on this camera system, so that hopefully the next time we meet online, right, through YouTube, I'll be able to get all the problems out of the works. Thank you guys for stopping in and listening to me talk, and I hope you guys are doing well, and I'll see you later. Bye.